Welcome to McMaster University's Chemistry Department, and we're standing here in front of the Atomic Absorption Spectrophotometer. An Atomic Absorption Spectrophotometer, or AA as we shorten it down to, is used for looking at certain amounts of trace elements in samples. And these can be environmental samples, or it could be the lead in paint that's used on a toy that you want to detect, or it could be a chemical sample that you've added a metal to and you're looking to see whether it was taken up in a tissue or whatever. So the samples, the elements that you're looking for are metals, and you have to ensure that the department, the person who has the AA instruments you're going to be using, actually has a lamp that has the same element of interest, because these lamps are actually created with a U or a tube of the metal in there that will emit in the absorbance range of that metal. The atomic absorption spectrophotometer then is looking for actually the atoms in a gaseous phase. So these aren't compounds. You're actually aspirating a sample up, and the atoms are going into a gas phase and then being excited in that burner. And as a wavelength of light specific for that metal is going through, it's absorbing as it excites and then falls back down to a stable state. And that's what the detector is picking up, is that absorbance. There will be we call it a cookbook. So there are many methods that are available for the elements that you're using. And in Varian, there's an area you can go into, and for example, if you're going to be looking at the lead in your samples, it will tell you what wavelength to sit on for the best absorbance readings, and it will also tell you the concentration range that you should be looking at so that you can make up your samples appropriately, and it will tell you the flow of that acetylene. So these are where we find out how we go about setting up our method. And luckily, we have these cookbook recipes that help us out to do that. For example, and I'll just move that aside so you can see the lamps. The Varian instrument, you're able to look at 4 different lamps at a time, not at once, but depending on where the lever is on this instrument, you can look at lamp 1, lamp 2, 3, and 4. Today we only have 2 that are installed in the instrument, a lead lamp, and this one is copper. With the flame off, the way that you align the lamp is by using what looks like a business card, but is actually designed with a target area that when you hold it in the burner range, you can see that the lamp emission is directly in that target area. And if it isn't, we can adjust the burner using various, you can grab it with your hand and turn it, or you can use the adjustment liner here. There is also an adjustment for up and down, but we can see from the positioning that in fact it's perfectly positioned, and we can continue on. So at this point here, we would want to light the burner, and that's how we optimize the lamp. So we're going to, our gases have already been turned on. As I said before, I will turn on the air and then the acetylene. And then we have a button here which shoots a small flame into the burner area. The gases are going up through the burner at the moment, and it starts the flame. So it sounds like a sputtering, and then as soon as it's kind of a continuous sound, you know your flame is lit. You can also see it to a certain extent through here. Then this is the capillary tube, which brings your sample up and into the burner. So all samples are in an aqueous solution, and the nebulizer is this area in here. And what it does, so that the capillary draws the fluid up, the nebulizer puts it into the gaseous form, and it's the atoms that are actually going into that burner and being excited and it's the absorption of those that is detected by your detector. So everything looks good there. I've got a nice flame going. The aspirator is drawing up my sample. And the next thing I would want to do is optimize my flame to make sure that everything is good. And we do that through software here. So other instruments, you may have a different interface to do the optimization, but for this one, it's done through help from the software. So it's asking me to check that the lamp turret is in the position of the lamp I want, and that my fuel and airflow is set properly. And again, if you see on here, you'll see where the red indicators are is where our gases should be set, and that's exactly where we have them. So the next thing we do is we click on Optimize Lamp, and now we have a green bar that is jumping up and down on the screen here. And the way we optimize is by, while looking at that bar, we actually adjust these two knobs on the lamp. And it'll just help to position that beam directly in the flame. So as much as we align the burner, we're now aligning the lamp. So if I just tweak these up and down, you'll see the green light is now going straight up. I can tell it to rescale, and we'll put it back down. And as I adjust, it continues to go up. And we're just trying to get it up as high as we possibly can. And now that we've done that, we're ready to start introducing our sample into the instrument. So we'll have set up the software with the method that we want. We'll have set it on a wavelength of interest that the lamp is set for. And then the next is to actually introduce your sample. So as I mentioned, we want all of your samples in the aqueous form. They can be a bit acidic. There may be some buffers in there. That's all fine as long as they're clear, colorless, and there's no precipitate at all. When you're ready to run your samples, the very first thing you're going to want to run is a set of calibration standards. So your calibration solution, you will start with your stock concentrate, say it's a lead solution, and then do a serial dilution of those. 5 solutions is probably optimal. That will cover the range that you're assuming your samples will fall in. So for example, here we have a graph that has a concentration in milligrams per liter, or ppm, and an absorbance range. And as I was mentioning earlier about our kind of cookbook recipes, most softwares and that will come with your atomic absorption spectrophotometer will have something like this to show you the range that you will need to make your standards in. So this one goes from 0 to 40 milligrams per liter. And you would set up your standards that span that range. According to Beer's law, you're going to get a linear response for concentration and absorbance within a certain range. And this graph is showing you exactly that. So when you're introducing your standards then, if your absorbances are increasing, or if they're doubling, say you had 5 milligrams per liter, and the next one is 10, and then 15, and then 20, and then 25. You want to see subsequent increases in absorbance that are matching that. And if you have software such as we do that will graph it as you're going along, you'll be able to see right away if you've screwed up on one of your standards, or you need to redo it again because maybe it started reading it before you were aspirating it. And it will be very clear to you whether you've done a proper job on your standards. Once you've got that nice linear calibration curve, when you put your sample in, your unknown that has that element, it will hopefully fall on that graph, and you'll be able to exactly determine, based on the absorbance, exactly how much of the analyte was in the mixture. So that is basically the setup and operation of the atomic absorption spectrophotometer. So I hope you enjoy your experiment.